Okay, this video is part 3 in our series on understanding solar photovoltaic generation and the controls they use. And we're also going to be using MATLAB and Simulink to help visualize and understand the components, but you really don't need either one to go through this series and to learn about the controls, but they are helpful so that you can model them and quickly see how they respond. Now, in this video, we're going to talk about a very important component that we briefly discussed in the previous video on phase lock loops, and that's an analog phase detector. And it's an integral part of the inverter control system. And we're going to be using this in the next video, talking about direct and quadrature axis conversions. And in order to do that, we're going to use an analog phase detector. And I want to make sure you understand how it works and how you can set it up and simulate it and what it does. It's going to be very important in our next video. So here I've got a circuit that uses a phase detector, an analog phase detector. And this is a circuit we're going to use in our next video, talking about direct and quadrature axis conversion. And at the tail end, we're going to have this phase detector. And you can see right here this block, which is a subsystem I've built, and it's a phase detector. Now, what this does, this block, is it has two inputs. And both inputs are just basic sine waves. And input 1 is a sine wave that is at a phase angle of 45 degrees. Input 2, in this case, is a sine wave with a phase angle of 0 degrees. So there's a phase difference between these two simple sine waves. And this phase detector will detect that 45-degree phase shift between the two sine waves, and it will output the number of degrees phase shift between the sine waves versus time out of this output, and we will put it into this scope. So we'll have a trace that shows you the degrees phase shift versus time for these two sine waves. And we also are tapping off to this multimeter device, which reads out the actual phase shift in degrees. In the second channel of the scope, we will just take both of the input sine waves and put them on top of each other using this multiplexer so that we can see the two sine waves on top of each other and the relative phase shift. Now, I'm generating those two sine waves in this circuit we'll talk about in the next video. And here up front, you can see we have set 45 degrees phase shift between these sine waves. And it goes through this conversion process and gives you these two inputs to the phase detector. So let me run this and you can see what we're going to get. Here on the top, as you recall, this is the output of the phase detector, and it tells you after an initial oscillation, at around 1/10 of a second, it flattens out at about 45 degrees. So it's telling us there's a 45 degrees phase shift between these two sine waves, and you can see just by inspecting that looks like about 45 degrees. So that's what the phase detector does. Very simple and very, very useful device. Now, I've built one pretty much from scratch because there really isn't one in the Simulink library. So I've made a subsystem, and inside the subsystem are these components. And as I mentioned in the previous video, in the phase lock loop video, the first two components, here's the inputs, the sine waves. I do a simple multiplication, just use a regular multiply block, and that gives you an output, and I then pass that through a low pass filter. So let me explain what that is and why we're doing it. Now, if you multiply two sine waves, you will get a result, an equation that looks like this, and it looks kind of complicated, but we're going to simplify it quite a bit. Now, there's two components to this output of the multiply. There is a 1/2 cosine 2 omega t plus delta phi, and delta phi is just the phase angle difference between the two sine waves. And so you can see there's a cosine 2 omega t. So omega is the hertz or the radians per second of these two sine waves. So you can see if these are 377 radians per second or 60 hertz, this will be a 120 hertz cosine wave in this component. So there's a double frequency component here. Here I am taking the difference between the frequencies of the two inputs, omega 1 minus omega 2, and I've got a 1/2 cosine of that minus delta phi. So you can see delta phi, which is the phase angle between the two, is in both components. Okay? So what we need is a DC. We basically just need a delta phi. Okay, a flat DC delta phi to tell us what the phase angle is. So this is a 2 times frequency, or 120 hertz in this case. So we can just filter that out. And that's what this low-pass Butterworth filter does. It takes this 120 hertz component and just filters that out. And I have a band pass of something around 50 or 60 hertz here. So 120 hertz will get filtered out. So we just get rid of this altogether. So now we're down to a 1/2 cosine of the difference in frequency of the two sine waves and delta phi. Now, if these are both 60 hertz sine waves, the difference is going to be 0. So this component is gone also. Omega 1 minus omega 2 becomes 0, and that component is gone. So all we're left with is 1/2 cosine delta phi, which is the phase angle difference. So now all we have to do is solve for delta phi in a 1/2 cosine delta phi, and we've got our answer in degrees, and we have to just convert it to degrees. And that's what these 3 blocks do. Okay, they calculate, they solve for delta phi, which means now you need an arc cosine and a multiple of 2. So we just take the output times 2, the arc cosine of that, which is the delta phi in radians, and convert that to degrees by multiplying times 180 over pi, and that gives us the number of degrees of phase shift between these two. So you can see this simple system just calculates the arc cosine of 2 times the input from the low pass filter, so 2 times this, and converts it to degrees by multiplying times 180 over pi. So that is a basic phase detector that converts 2 sine waves with a phase shift to a number of degrees between them. So all you need to do is take that, convert it to a subsystem, and you've got your result. So that is basically a phase detector. It's a very simple system, and takes advantage of the fact that you can filter out some of the components, and it takes advantage of the fact that these two sine waves are of the same frequency, and that greatly simplifies the detection of the phase angle. So that's basically a phase detector. I hope that's helpful. Take care and have a really good day.